Hello everyone. For project 3 we implemented sound generation using DCGAN using 3 different approaches. Each approach is explained in a separate interactive IPython notebook file which is present in our GitHub repo. In this video we will give you an overview of approach 2 to generate sound using DCGAN. In order to run the code for our approach 2 you would need to download our GitHub repo and copy the drum_beats interactive Python file and the drum2beats folder into the root folder of your Jupyter notebook. Once you run the drumbeats interactive Python file, you get the following notebook. In this method, we have taken a music data file called drum2.wave, which is saved in a drum2beats folder. This drum2beats.wave is split into 32 images, where each image represents the frequencies in time corresponding to one beat. The drum2beats file is recorded at 92 beats per minute and is 21 seconds long. And the following code gives you an overview of how the sound file is converted into the grayscale images. These grayscale images are then trained on a DCGAN. The outputs of the DCGAN are then recovered back into sound. Do note the process of training of the DCGAN is done through a separate Python program and is present in the sound DCGAN folder. This notebook will explain the steps to follow how to train the DCGAN outside the Python notebook. For the purpose of this demo, I'm not going to go through the training. I'll just show you the code where the training is explained. So let's go to the code. So in this part of the code, we are just importing the necessary packages. This part of code has certain filters, functions which limit the low cut and high cut frequency of the data before it is passed through, before it is converted into grayscale images. There are other functions such as pretty spectrogram, invert pretty spectrogram, etc., which are used to generate a spectrogram of the image data when it is generated from the generator of our DCGAN model. This was just another technique we used to see if we can reduce the noise which was present in the output of the sound which of the images generated by the generator. These are certain parameters that we require to run the code. Here you can see beats per minute is 92, which is the beats per minute of the drum2.wave file. Then there's a low cut frequency and high cut frequency. In this part of the code, we are reading the drum2.wave file, calculating the number of seconds, finding the rate, finding the number of beats in the length of the sound file, then limiting the sound file into 21 seconds, extracting the frequency data. Here we're clipping the data into a length of 9,24,800 frequencies. This is because we have around 32 beats in this 21 seconds. Then we are splitting the data into samples whose length is equal to approximately 1 beat of the music file, and if we play the music file, this is how it sounds like. Alright, so now here we're taking each sample and saving each sample in the drum2beats folder with the name of gray plus I, the sample's number, and as a grayscale image. And if we run the first sample, that is the first beat of the music, this is how it sounds like. The following code explains how to train the DCGAN on the images generated from the drum2.wave file. From the 32 images which are generated in this case. Before training, you have to save the images into a TF records folder. So these are the steps to save the images into a TF records folder, and these are the steps to train the DCGAN on the images contained in the TF records folder. For the purpose of this IPython notebook, training is already been done, and the results of training are already saved in the drum2 beats folder. So you can just run the IPython notebook, continue running the IPython notebook without training. So in this part of the code, we're taking an image generated by the generator for the 6,100 iterations. We're reading the image, we're reshaping the image, we're into a one-dimensional tensor, and we're playing the sound extracted from the image. Again, we take another image. Let's say this is the image after 6,200 iterations of training. Here again we are reshaping and rescaling and converting into a wave spectrogram and playing the data recovered from the image. Similarly, this is data recovered from image generated by the generator after 6,400 iterations, and this is the sound generated from the image generated by the generator after 7,500 iterations. So if we combine the sounds and play the clip of the combined sounds, this is how it sounds like. We do see that the sound is a little noisy. However, the sound does pick up certain characteristics of the drum beats. Although they being noisy, we did try to look into various techniques of how to reduce the noise. Now, one of the techniques we tried to reduce the noise was to scale the images in a different way by scaling them from a domain of the minimum frequency of the entire sound file, from a range of the minimum frequency of the entire sound file to a maximum frequency of the entire sound file, and then rescaling them back into that frequency range when the images were generated by the generator. However, such an approach did not give the best results. Another way we tried to recover sound from the noisy output is in a better way is we tried to train the generator for a longer period, the DCGAN for a longer period of time. However, this just ended up in the DCGAN being overtrained and the images produced generated in sounds being similar and one-dimensional. The third way we try to recover sound from the image is to convert the data of the recovered sound, data of the recovered image into a spectrogram, and then converting the spectrogram into a sound. So here is the example spectrogram which is generated from image generated after 6,100 iterations, which is the first output above. Similarly, the spectrogram for the second output, the spectrogram for the third output, and the spectrogram for the fourth output. Now if we recover the sound from this spectrogram, we see that the sound is something like this. So we see that the sound is more amplified, and it is still noisy, but it's more loud and clear. The sound generated from the second spectrogram, sound generated from the third spectrogram, and the sound generated from the fourth spectrogram. So here we do see that the sounds which are produced do have slight characteristics of the input data. they are very noisy. So if we do look into certain ways of denoising the the sound generated from the images, then I think we would have better outputs. However, this can be a future scope of the project, and given an opportunity, we'll try to look into a way into doing this. The sounds generated from Approach 1 and Approach 3 are better than the sounds generated from drum beats. That's because we believe that this DCGAN does struggle for in generating sounds for lower frequencies. Thank you. That's it for this video.